Hi, let us continue our discussion on three-phase induction motor. We know that in case of AC machines, that is either in synchronous generator or in a three-phase induction motor, this conductor will be static and the magnetic field will be rotating, right? So let us understand the concept of rotating magnetic field and how it is being produced. Okay, so we know that in three-phase induction motor, the stator has three windings and which may be connected either in star or delta form, and the windings will be displaced from each other by 120 degree. Okay, and whenever we pass the current through the winding, the current flowing through each of the winding will produces the flux, and even the flux produced in each winding will be having 120 degree phase shift. Okay, so this is what the diagram which indicates the phase shift between the fluxes produced in each phase. If we consider the phase sequence as R by B, so this red line, it indicates the flux produced by the phase R, and yellow line, so we can observe that. So it is starting here 120 degree. So that is, if the R phase produces the flux which can start at 0 degree, then Y phase will produces the flux which can start at 120 degree apart from the phase R. Therefore, and also the phase B will produces 120 will produces the flux which is 120 degree lagging compared to the phase Y flux. Okay, so this is what the waveform for the fluxes produced by the three phases, and also we can represent these fluxes with the help of the phase diagram. So this is what the phasor diagram. So this arrow line, red line, the vector, it indicates the flux produced from the phase R. So we represent it as phi R. And yellow line, this is the vector which represents the flux produced by the phase Y, that is phi Y. And the blue line represents the vector of the flux produced by the phase B, that is phi B. Okay. Right. So we can write the expression for the fluxes produced from each of the phases. So flux from the phase R is equal to phi m sin omega t, and from phase Y, phi y, it is phi m sin omega t minus 120 degree. That is, compared to phase R and Y, there should be 120 degree apart. So we can write phi m sin of omega t minus 120 degree. And the phase B should produce the flux which is 120 degree apart from Y, and 240 degree apart. It should lag by 120 degree compared to phase Y, or it should lag 240 degree compared to phase B, phase R. Okay, so that is, there should be a 120 degree phase shift between the flux produced by phase R and Y, and 120 degree phase shift between the flux produced between Y and B. Okay, so from phase R, the flux produced is phi m sin omega t. From phase Y, it is phi m sin omega t minus 120. From phase B, phi m sin omega t minus 240. So we can also call omega t as a theta. Phi m represents the maximum flux produced in each of the phases. Okay. Now, in order to understand the rotating magnetic field, let us take the different position of the flux, and we will see how it actually rotates in the space with the help of vector diagram. Okay, so to start the analysis, let us consider the first case, that is at theta is equal to 0 degree. Okay, at theta is equal to 0 degree, we will see what will be the total flux. Since they are AC component, we will get the total or the resultant flux by performing the vector addition of the three fluxes. Okay, so at 0 degree, substituting in the first equation, phi m sin 0 it will be 0, and in the second equation, that is phi y, it is phi m sine of minus 120 degree, which will be minus root 3 by 2 phi m, and the third one, it is sine of minus 240, it gives plus root 3 by 2 sine, phi maximum. Okay, so when we add these three, we will get the resultant flux as 1.5 times the phi maximum. Okay, and right. We can draw the vector diagram of these three fluxes. The resultant flux is produced with phi y and phi b, right? So phi y is minus root 3 by 2 phi maximum, that is, it is negative. Phi b is positive. So we can just draw, this is a phi y and this is minus phi b. Sorry, this is minus phi y and this is phi b. Okay, so this is minus phi y and this is plus, this is positive phi b and negative phi y. Okay, so here you can observe the negative sign, and the resultant of these two flux is nothing but phi r, so which is 1.5 times phi maximum. Okay, and okay, so we can also just do one more thing. First, considering theta at 0 degree, consider all the three equations and substitute theta as 0. We will get these three values, phi r, phi y, phi b. And let us draw the vector diagram for that. We will get like this. And just dividing this triangle into half exactly, considering this triangle, you can find the total flux produced, and which will be equals to 1.5 times of phi maximum. Considering this triangle, we will get, that is cos of you can say A, B and C. This is 30 degree. From here to here it will be 60, and this is 30 degree. So cos 30 will be equals to so this length divided by this length divided by this length, adjacent divided by hypotenuse, and so adjacent it is this length divided by 2, and so the value of this hypotenuse is root 3 by 2. When we simplify them, so we will get the value of total flux as 1.5 times phi maximum. So by looking into this diagram, what we can say is the magnitude of the total flux produced is 1.5 times phi maximum, and its position is vertically upward. Okay, now let us take the different position of the flux, that is consider theta at 60 degree. So now we will substitute 60 degree in all these three equations. The first equation becomes phi m sine 60, second equation becomes phi m sine of minus 60, third equation becomes minus 180 degree. Okay, so the first two fluxes phi r and phi y value is root 3 by 2 phi m. Phi y is minus root 3 by 2 into phi max, and phi b is equals to 0. So phi r is this one, positive flux. Phi y is negative. So actually the negative value of the phi y, so we can just indicate like this, which is shown here with an yellow line, and the resultant of these two flux is phi r. Okay, and here the total flux which we can calculate as 1.5 times phi maximum, which is obtained by the vector addition of phi r and then phi y. So here, by looking into this diagram, what we can see is the total flux produced is 1.5 times the maximum flux. But the position of the flux is now it is moved in space in clockwise direction with an angle of 60 degree. Compared to this diagram and this diagram, the first diagram was vertically upward, and then now it is moved like this, rotated to 60 degree in clockwise direction. Now let us consider theta is equal to 120 degree. So we will substitute theta as 120 in the three equations. We will get the values like this, and by plotting the phasor diagram, and you will again obtain the total flux as 1.5 times of maximum flux. And in this time you can see that it is moved downward little bit, that is clockwise direction it has rotated. So by looking in similarly, again you can just consider theta at 180 degree. So it would come vertically downward exactly at 90 degree, minus 90 degree, and then like this, and then it will come like this here. So what we can observe from these three diagrams, just notice first vertically upward, then it is tilted to right side, and then further tilted in downward direction. So what we can observe, the magnitude of the flux produced is same, but it is rotated in space with an angle of 60 degree in a clockwise direction. Okay, it has rotated through 60, or you can say 120 degree in space in a clockwise direction. Okay. Right. Now, what is speed of the rotating magnetic field? Okay. The speed of rotating magnetic field we represent with ns. As there exists a fixed relation between frequency of the AC supply and field winding and the number of poles, so which we can express with this expression, that is ns is equal to 120f divided by p, because the number of poles in stator and the rotor will be same. For the standard frequency, whatever the speed of rotating magnetic field will result, we call it as synchronous speed. Thank you.